Okay, it seems to be working. Maybe you can start sharing your screen.
Yeah, so I should have asked that before, but for how long am I supposed to present?
You have 45, 50 minutes.
Okay, awesome.
People
Yeah.
can interrupt you if they like to ask questions during the talk.
Okay. So let me so what are you guys seeing here? You guys are seeing the wrong screen, right?
Mm-hmm. Yeah, we're
Okay.
seeing everything.
So let me just stop sharing. Let me share. Let's talk to. Okay, what about now?
Yeah, now we see only a single slide. Cool.
Okay.
Okay, so good afternoon or good evening, everyone. We are back to our quantum matter seminars, and today we have the pleasure to have Denis Candido from Iowa, and he's going to talk about solid-state platforms for quantum information science. Thank you very much, Denis, for accepting your invitation, and feel free to start.
Yeah, so let me thank you very much, Krisha. Let me just like change things here so I can take a look at the camera while I am delivering the seminar. So let me just do this. Okay, and I think, yes, okay, perfect. Can you still see the main presentation, right?
Yeah.
Okay, perfect. So hello, everyone. So first I'd like to thank Krisha for inviting me. So this was a this is a very good series, and I really do appreciate the initiative during the pandemic to put this together. So that was like something that I was like always trying to follow in order to not get bored during this difficult pandemic time. So I really appreciate having some space here to talk about a little bit of what I have been doing in the last years. And well, the main subject of this work that I will present, it's a qubit, okay? So which for our case, it's given by spin defects in solids, okay? For example, defects in diamonds or defect in silicon carbides. And although these spin defects, they have very long lifetime, they still like face many problems. And one in particular is the coupling between different spin defects over readable distance. And so this is what I'm going to be trying to tackle. Okay, so how do we solve this problem of coupling and entangling solid-state spin qubits? And most of the results that I will discuss here, they were done in collaboration with Professor Flatté from University of Iowa, Greg Fuchs from Cornell, David Oshalom and Masaya Fukami from University of Chicago, and also Ezekiel Halperin from Ohio State University. Okay, so the idea of the seminar is to first introduce the qubits used in these works, and then I will describe and show some of the problems and difficulties that our type of qubits face. And after that, I will show how we essentially propose to resolve this problem. And towards the end, I will describe some directions that I find very interesting to be investigated. And if time allows, I will try to comment more on that. Okay, so let's start with our first bullet point. So, and so it's about qubits, of course. And before diving into our qubits, I would like to revisit, like very quickly, the concept behind classical and quantum bits. So, of course, starting with the classical bits, we know that bits are the fundamental concept, if you will, of classical computation and classical information, and they're kind of the basic units of information used in most of the computing and digital communications, and probably in all of them. And as we know, a bit, it's a logical state, and it can assume one out of two possible values, which is being represented here by by the green ball or the zero or the red ball or the red dots. Okay, so in classical computer, this the bits are taken by the computer. They are processed by the classical components of our computing using arithmetic and logical operations, and then they are returned by the computer as an answer, typically also written in terms of bits. And so everything in classical computation is done in terms of bits. So now, in what regards the quantum computing, now everything is done in terms of the quantum bits, or what we call qubits. And for this object, for this qubit, the story is a little bit different, okay? Because now qubits, they're, instead of only assuming two possible values, now the qubit is defined by superposition of two different states, okay? And here the superposition of these two different states are essentially the cat0 and the cat1. And here we have like two different coefficients, alpha, beta, to give different weights to this superposition. So, and just like by recalling that states in quantum mechanics, they must be normalized to 1, we can interpret, like, for instance, this alpha and beta squared as being represented by the length of the sides of these triangles that I'm showing here. Okay, so this is like visualization of the qubit, essentially like show us that there's an infinite number, okay, along the circle in which our qubit state can assume. Okay, so and again, just to contrast with the classical case here would be only the north or the south pole, while again the quantum bits or the qubits, they have this infinite possibility of places to be. Okay. Another interesting property of qubits is the entanglement, which it's presented in a system if we cannot rewrite the total wave function of the system as the cross product of the wave function of the qubit A times the wave function of qubit B. And here on the bottom right, we essentially have like one entanglement state on the left-hand side. And of course, it's easy to see that we cannot rewrite this as a cross product between psi of A and psi of B. So this is what we call like entangled state. And I do not want to spend much time on this, but the superposition of the superposition character of the wave functions with the entanglement of wave function states, it's what made quantum computing area like so interesting and so adventurous. Okay, so due to these two different facts, we can, for instance, like prove different interesting properties. Which, for instance, we can prove that it's impossible to copy general and unknown quantum state, which people in the call as a quantum cryptography, and this goes by the known cloning theorem. And also we can like prove that it's possible to use a quantum parallelism for like faster number factorization using, for example, a Shor's algorithm. And these are the main reason why so many companies are investing on fabricating their own quantum computers during this last 1 or 2 decades. Okay, and well, and do not take me wrong, I think that those are like great and exciting things for our field. But as a good theoretician, why should we care about it? Well, and we essentially do care about it because we're also interested in addressing fundamental questions of quantum mechanics, right? So like study entanglement, measurement of Bell's inequality, superdense coding, and etc. So it's really nice for us to have a practical and also realistic system to kind of like probe and study this like fundamental questions, right? So it's also very interesting from a fundamental point of view to have systems easily to probe the quantum mechanical properties. So now, like back to the qubits, the first qubits introduced in condensed matter area, they were obtaining using gallium arsenide quantum dots, where these qubits are given by the state of individual electrons confined by electron gates, which are represented here by this like a grayish region. So here there's like gates, and then you can control this gate, and essentially you control how many electrons you have here. And not only how many electrons you have here, but you can also control the interaction between two electrons that could be placed, for instance, like here, or even like within these two different circles. Okay, so those were like the first types of qubits proposed with condensed matter system, and here they call it just like target and control, because this work was done in the context of the CNOT gate, but that's not really important for us. What's important is that later people also extended the idea of quantum dots in semiconductors, but instead of working with electrons, now they also extend this idea to work with holes. And by holes here, I mean just like a missing electron on the valence band. Okay, so so let's just like dive in for the people that are not very familiar with. So if we like solve the Schrödinger equation for electron in a box, this is what we're going to find. So we essentially have like a lot of discrete energy levels, and of course we know that the separation, energy separation between consecutive levels is proportional to 1 over r squared, where r is essentially the length of your well. And however, all those levels, they are degenerated with respect to spin. Okay, so if we want to lift, this is spin degeneracy. We need to apply a magnetic field. And so by applying this magnetic field, we're now able to obtain these energy levels that are separated from each other, and there's no degeneracy. And now we can, for instance, choose 2 of these levels to represent our qubit. And this is, I chose to like represent our qubits by those 2 different levels here. So this is essentially how like people are using quantum dots, they are able to define their qubits. Okay, so and for the systems, we have a qubit radius around 50 nanometers, and here to cause like a reasonably large spin splitting, we usually need to apply magnetic field from 0.1 Tesla to 1 Tesla, and it turns out that if we use like these values, you can see that the energy separation between these 2 qubit energy levels, it's going to be very small. And this is like a problem, because our qubit could be easily thermally excited, okay, that's like messing with the initial information of our qubit, and also messing with possible controls that we want to do with this qubit. Okay, so therefore, to really like push a qubits in condensed matter system towards a more realistic and more like robust setup, we need to make shorter qubits. Okay, and here, just like to give a rough estimation, so for those type of quantum dot qubits, due to this large qubit radius, the operating temperature for those qubits, it's around like 100 of millikelvin. Okay, so we really want to like push this forward to like kelvins, or maybe like qubits at room temperature. So because with 100 of millikelvin, this is like not practical at all. So the main question like for this field in the last years have been, how do we improve this? Okay, so how can we make qubit energy levels like more robust? And as I said, we just need to decrease the radius of the qubit. So, but how do we do that? We cannot do that with quantum dot. Well, so then, following this works from this quantum dot works, we also like saw some experiments on manipulating and controlling of donor impurities in silicon. And here, of course, we have a shrinking of the qubit radius to around like 5 nanometers, because they are donors, right? So, and with that, we can essentially like raise the operating temperature like to roughly like 5 kelvins, and 5 kelvins. Yeah, and of course, again, just like recalling, this is simply because you're increasing the energy separation, so the system becomes more robust again against thermal excitations. And then finally, recently, in the last 10 years or so, we have seen defect spin centers in solids, like for instance, nitrogen-vacancy in diamonds and divacancies in silicon carbides. And for instance, in nitrogen vacancy centers, or NV centers, as I'm going to be calling during this through the end of my talk, the electrons are confined around this like vacancy region, as we can see here on the screen, thus having a couple of angstrom of qubit radius, okay? And this combined with their deep in energy levels, as shown by this graph on the right, we can actually see that the operating temperatures for those types of qubits, it's going to be around the room temperature and even beyond. Okay, so that's like a very interesting system, and that's the system that I'm going to be focusing here. Okay, so and just to give a more complete description about this spin centers and solids. So here we have, for instance, the nitrogen vacancy diamond, and which essentially is just you have like a diamond lattice. You just substitute a carbon atom by like a nitrogen atom, and you just like remove a carbon atom nearby. Okay, so this like blue thing here represents just like the absence of like any atom, what we call like vacancy. Okay, and for the silicon carbide, the story is a little bit different. There's no substitution of atoms, but rather just like removing two atoms that are adjacent to each other. Okay, and what I always like to say that what is very like ironic in physics is that we usually push for perfect systems, right? We always want to work with systems without imperfections and etc. While it's for quantum information science application, it's really the system with defects that present this like very interesting properties. Okay, and of course the takeaway message is like to also important to abandon perfection. Okay, so in the past, so going back to the qubits, so this type of qubits that I'm going to be focusing, in the past few years, they have received a great and also fair, in my opinion, attention due to their many applications, okay, including quantum sensing, quantum information science, and quantum memory. So here, for instance, we can see this new archive that was recently posted where they could obtain a 5 seconds coherence time for a single qubit, okay? And again, just like to emphasize why these spin centers, spin defects are so good for quantum information. Well, first, because of their energy states are very separated from each other, because of course they are very localized. So they're robust against thermal excitations. And the second point is, since this is a very localized system, this system is not going to be very susceptible against disturbance of our environment. Okay, so that's let's say that's the two main reasons that make this type of qubits are very useful and interesting for us. Okay, so now let's understand why these diamonds are very interesting from the practical point of view. Okay, so essentially, if you focus on the ground state of this qubits, we're going to see that this is going to present a spin 1, okay, system, and as I said before, we can lift the degeneracy of this plus and minus 1 state, for instance, by applying magnetic field, okay. But if you do not want to apply any magnetic field, we can also work with this qubit without the magnetic field. So this is like again another advantage of this type of qubits, because here we say that they are this is a spin qubit addressable without the need of like a magnet to shift or to lift the spin degeneracy. Okay, so and the other interesting feature about this, it's this 2.8 gigahertz of microwave frequency of spin split between the ground state and this, the spin, the ground state of our spin 1 system with respect to the excited state. Okay, and why a microwave frequency? Well, microwave frequency is like very convenient, right? Because then you can manipulate this qubits, initialize this qubit using like microwave antennas, which again is like very practical. So this is like the two like main interesting features about this. We can control the spin qubit using a microwave, and we don't need to use a magnetic field to have this initial split between the two levels or the three levels. And but of course we can also apply magnetic field, and with that we can tune these energy levels, and they respond not only to the magnetic field but also to the electric field. So and if we apply, for instance, a magnetic field, the what we call the zero magnetic ratio, it's going to give a splitting of roughly 2.8 megahertz per Gauss, which makes the system very powerful, as we essentially do not need to apply very strong magnetic fields to produce reasonably large field splittings. Okay, and I'm going to comment more on that sooner. So now if we take a look at the complete energy levels of the center, this is what we're going to find. So so this system has a triplet ground state and also a triplet excited state. And actually what is interesting about the system is actually we can populate the excited states by using ordinary beam laser, as is shown here by this image. And this is like very practical and good for experimentalists. And most interestingly, due to this like metastable intermediate state that we have here, which essentially creates a detour for the electrons on the excited states, it's possible to initialize the system into a well-known state, here given by ms equals to 0, just by applying this laser. Okay, so we can essentially apply green laser on these spin defects and we initialize our system into ms equals to 0. Okay, due to this like detour, and then we can use microwave to create gates to use and make quantum gate operations and etc. And interestingly, the read out of those qubits, it's also performed by shining laser. Since if we have the initial state in the 0 state and we shine laser, we're gonna obtain a photoluminescence shown over here, and because of this spin conserved frequency transitions, and for this reason we call this ms equals to 0 at the bright state. But on the other hand, if we have now our qubit is initialized in the plus or minus 1 state, we're most likely to not observe a photoluminescence due to this detour that I mentioned previously. And for this reason, this plus or minus, they're called the dark state. Okay, so this is like something very interesting from NV centers. They are not only optically initialized, but they are also optical read through each bright and dark state. Okay, and the combination of all of these good properties, it's what makes this NV centers not only good candidates for quantum computing, but also good candidates for quantum networking, and also quantum repeaters, as you essentially are combining a optical transition to a local qubit with microwave frequency. Okay. And there's like another interesting feature about these NV centers. So for instance, if we bring this NV center close to a surface which produces a magnetic or electric field, the frequency of the defect of our spin center and this spin center is going to shift. And by contrasting this photoluminescence before and after bringing then the center close to the surface that we're probing, we can calculate the magnetic and electric field or infer with precisions of angstroms. Okay, so this is basically the other great application of spin defects. They also like are great for quantum sensing. Okay, so far I have seen So far, we have seen that spin defects are great qubits with long lifetime, easily to be initialized, manipulated, and read out. But life is not so easy, and this brings me to the second part of my talk. Where I will comment more about the problems of using spins defects as qubits. Okay. So again, spin defects are qubits with long lifetime, easily to be initialized and manipulated, and this basically fulfill 4 out of the 5 requirements for practical quantum computing listed by Vincenzo. And as we can see, there's still one item which we did not talk about, which is the scalability, right? So, and what this is basically telling us is that if we only have one qubit, we cannot do anything. We cannot realize entanglement, neither measurements of Bell's inequality, nor make quantum computing. So, a long story short, we need to have like many qubits. And not only we need many qubits, but we need them to be coupled, and we need them to be entangled, okay? So the natural question is, can we have coupled and entangled NV centers in diamond? And it turns out that due to this due to the weak magnetic dipole-dipole interaction, different NV centers can be entangled, okay? There's no problem with that. However, only if they are distanced by distance from each other by roughly 20 nanometers. Okay, otherwise the weak dipole-dipole interaction vanishes, and you're not able to establish this coupling and entanglement anymore. However, if these NV centers they are coupled by if they are distanced by these short distances, it becomes difficult to optically read and address these two NV centers simultaneously and separately. Okay, and this happens essentially because of the fluorescence of because of the overlap of their fluorescence. So we really cannot distinguish which NV center is emitting or has emitted a photon. Okay. Additionally to this point, if we consider that the size of the laser spot have at least hundreds of nanometers, by shining green laser on our sample containing different NV centers, we would essentially have something like this instead of something like this. Okay, so by trying to initialize and read one NV, we would be directly massing and affecting the other NV center. So, so from here, we clearly see that the importance of having coupled and entangled NV centers separated by distance larger than the laser spot. Okay, and this is actually the main problem of using and having NV center as a qubit. Okay, so this brings me to the second or third part of my talk, where I will describe how to overcome the difficulty of not having what we call naturally coupled NV centers over safe readable distance. Okay, so and in order to solve this issue, we say that the interaction between two NV centers must be assisted by something, or in other words, we need another system which can propagate and transport the information from one NV to the other NV. And this is what we call in our field as a quantum bus, okay? And this can be done, for instance, by having a hybrid quantum system made of our two NV centers coupled through a medium, as for example, optical modes of a optical fiber, okay? And for example, in this work here, the communication between these two NV centers was done through real photons. And here they could verify, for instance, the violation of Bell's inequality for NV centers separated by 3 kilometers approximately. An alternative way to solve this problem was proposed by this work, Luca and Daniel Loss, where now instead of having like these photons mediating the information, now we're going to do this mediation of information through the exchange of virtual magnons. Okay, so Our proposal is going to be based on this on the previous proposal that I showed. However, here we're not going to work with virtual magnons, but rather real magnons. Okay, so here magnons is really going to mediate this interaction between NV1 and NV2, and magnons are going to form a quantum bus. Okay, and to have the success of our proposal, we essentially need to engineer a strong and resonance coherent coupling between NV spin and single magnon mode, as indicated by this picture. And again, the main difference between our proposal and the previous one involving virtual magnons is that now real magnons are really transporting this information between NV centers. And I'm going to discuss a little bit more about that later. And these magnons, for instance, they can be created by a driving microwave field. So in this sense, by having the success of our hybrid approach, we would only not have establishing a quantum transduction between NV and magnon, but also a quantum transduction, for instance, between a microwave frequency of quantum processors and quantum optical networks using NV centers to using NV centers coupled to the magnon mode. Okay. So far we have introduced our idea. So now let's see how we can make this a realistic proposal. We choose so this is like our setup. Okay, so this is the setup that we're going to be focusing on this work, and we choose our setup made of like magnetic disk on top of 111 diamond substrate with out of plane magnetic field. And in order to succeed with this proposal, we essentially need to achieve 3 different ingredients. So first, we need to have a coherent NV spin, which means that we need to be able to assess and manipulate the information of the NV spin before we lose this information. The second ingredient, we also need to have a coherent magnon mode at low temperature. Otherwise, the information is going to be lost when being carried by the magnon. And finally, we also need to achieve this, as I said before, this strong coupling between NV and the magnon mode. Okay, so this is what we essentially need to achieve to get the success of our proposal. So, and regarding point number 1, we have to keep in mind that the closer we move to the surface, the stronger it's going to be the decoherence. So we really here want to focus on NV centers that are not that shallow, but also not that deep, because if the NV is very deep, it's not going to experience the magnon field very efficiently. So, so we really want to have some like intermediate depth, as we call, in order to make this proposal practical. And actually, we can see that for isotopically pure diamonds and the centers located at roughly 20 or 30 nanometers, we can obtain coherence times of around 1.5 milliseconds as presented in all of like this 3 different words. So this ingredient 1, it's kind of like it's reasonably fine for us. So now let's focus on the ingredient number 2. And let me say that this ingredient, it's a little bit like challenging because, for instance, one of the most common materials, which is the YIG, most common magnetic materials, shows an increase of the magnon damping or the magnon lifetime, or 1 over the magnon lifetime at cryogenic temperature, as can be seen over here. So, so this is what this is saying, that if we want to operate at low temperature, the magnon lifetime is going to diminish, okay, for this material YIG. And so this is like one point against the usage of like this material. And also this YIG is a crystal. So if you want to really build a hybrid structure, we're gonna have this lattice mismatch problem, okay, of growing YIG on top of diamond, since they do not have the same crystal lattice, there's going to be lattice mismatch, and this is going to like produce a lot of like noise around this interface, which is going to be coherent, okay, our system. So for this reason, here we proposed a organic ferromagnetic material that's called VTCNE, and this material has a low magnetic damping comparable to YIG also. And however, since this is an organic material, we can overcome the second difficulty of working with WIG, which is the implantation of the crystal on top of diamond surface, okay? So here VTCNE can be easily patterned on top of any substrate, and as can be seen here in this image, we can even like choose a different forms, and this material has been like carried and has been developed by Ohio, mainly by Ohio State University, group of Ezekiel Halperin. And as we've shown here in this paper, actually we see that VTCNE recovers the magnon lifetime, the room temperature for the magnon lifetimes at cryogenic temperatures. Okay, so we're not going to be like facing this issue of increasing decreasing magnon lifetime once we reach the cryogenic temperatures. So how do we obtain the magnetic? How do we obtain the magnons modes of our system? Well, the magnetic dynamics of our system is essentially described through the solution of both Maxwell's and Landau-Lifshitz equation of motion. So I'm not gonna give a lot of details here, but I just want to say that if we like focus at low temperature and we apply a magnetic field, we know that all spins are going to be frozen, pointing parallel to the direction of the external field. However, this type of magnetic fields also have excited states, okay, which are called the magnons. Magnons are essentially, or spin waves, they're essentially the excitation of these modes of magnetic material. So for instance, the lowest magnon mode is when all the spins are precessing in phase around the direction of the magnetic field, but we can also have even more energetic magnon modes, which have this interesting like spin oscillations that really like resembles a wave, and again they're called as spin waves or simply magnons. And here I'm running a little bit out of time already, so I just want to say that we do understand the magnetic and the magnon properties of this VTCNE material, and this is essentially shown in these two different works, and we can like solve this analytically using Landau-Lifshitz equation together with Maxwell's equations for magnetic material. And the only thing that I want to say is that here we're going to be focusing on magnon modes that have a large amplitude around the disk, okay? And this is simply because if we want to use the coupling is going to be proportional to the magnon fringe field, and we do not want to have a magnon fringe field that is extended throughout the whole quantum dot, but rather confined, because this essentially decreases the effective volume of the magnon and therefore increases the coupling rate, as the coupling rate is proportional, right, to 1 over square root of the effective volume. Okay, so ingredient number 2, it's also achieved. So we do have coherent magnon modes able to transmit this information from one qubit to another one. So since we have accomplished these the two first ingredients, now we move to the last one, which is the strong coupling between spin, NV spin and the magnon mode. So, and to understand this, let's just like recall that in the absence of magnons, this is the Hamiltonian in the presence of a DC magnetic field, which contains eigenvalues plotted below. And now if we add the interaction of the NV spin Hamiltonian with the magnons, this is going to be described by the Zeeman Hamiltonian. And for our case, it's convenient to separate the dynamical fringe field modes as a sum of the right and left circularly polarized fields. So after performing the rotating wave approximation, we see that while the right circularly polarization of the fringe fields allows for the coupling between the +1 and the zero state, the left one allows for the coupling between the -1 and the zero state, okay? And maybe a more intuitive way to understand this result is by noticing that, for instance, the spin projection of a linear combination of -1 state with zero state rotates in the same direction as the left circularly polarized field. So from the rotating frame of the electron, the left polarization is static, which in turn is going to lead to like a stronger coupling as compared to the right polarization of the field, which oscillates very fast on time. And so now if we plot now the magnon frequencies as a function of the external DC magnetic field, we see that we do have like a resonance condition between magnon frequency and NV transition. And this is essentially the interaction between the red energy branch with the magnon modes. It's going to be like the subspace that we're going to be focusing on this work. So here I'm just like essentially plotting the fringe field for the high angular magnon mode at 30 nanometers below. And although it looks like we have only a circularly polarized, okay, here we go, we can actually separate its components. And when we separate its components, we really see that we do not have like only one polarization, but rather two different polarizations, okay? And we can also write the interacting Hamiltonian between NV spin and magnon mode using second quantization language. And this is its form after applying the rotating wave approximation, where here the term G is essentially the coupling rate, and this is again a proportion to the fringe field of the magnon. So this is why we want to have very concentrated magnon modes, because this is going to produce a larger fringe field, which in turn is going to produce a larger coupling rate. And of course, the sigma are just like the raising and lowering spin operators with respect to -1 and the zero subspace. So let's just like understand physically what kind of physics is contained within this Hamiltonian. So if we start, for instance, with two NV centers, one in its excited state and the other one in its ground state, and also like a magnet with no magnons excited. So if we start with this system and just let this system to evolve, we'll first obtain a decay of the NV center 1, followed by the excitation of our magnon, right, in our magnonic material. And after that, this magnon is going to interact with the second NV center, okay, and this is going to be followed by the excitation of the NV center, the second NV left, okay, and the destruction of the magnon mode. So this is essentially what we're gonna that's what we want to produce, right? This coupling and communication between these two NV centers. This is just like a more like intuitive visualization for that. So so the only thing that we have to verify now is whether the strong regime, as we call, can be achieved here or not. And to calculate that, we calculate the cooperativity, okay, which is essentially quantifies how often the magnon spin can coherently swap information. Okay, so and this is essentially written as the magnon spin coupling rate divided by the magnon damping rate times magnon spin coupling rate divided by the NV, the coherence rate. And of course, if we have strong coupling regime, if you have, cooperativity larger than 1, then we can say that we do have our system in the strong regime, and therefore the spin and magnon, they're going to be able to exchange a lot of information before this information gets lost, okay? So here I'm just like plotting the cooperativity at a 30 nanometers plane below the diamond surface, and as we can see, we do like achieve a cooperativity larger than 1 for a wide spatial region, which is larger than the NV implantation precision, and here just like other plots to show that this is like a very robust system rather than just like a fine-tuning type of thing. And I'm just gonna, I'm sorry, yes, please go ahead. Okay, so I think that he unmuted himself. Okay, so I'm just like gonna continue, I think. Yeah. Are you guys, is everything okay?
A question, feel free to unmute yourself.
Yes, please, go ahead. Okay, I think I will just continue. I don't know how to deal with that, Christian. I'm just gonna continue.
Yes.
I think.
Okay.
Okay. Yeah. So oh my God, I understand now. I'm sorry. Yeah. Okay. So okay. So okay. So again, cooperativity larger than 1 is obtained for the system, and we essentially say that this type of proposal um, um, it's going to succeed in principle, experimentally speaking, and this work here was published in this material, Quantum Technology, which is a new magazine published by the London College in England. And we also have extended, for instance, this, and here I'm just going to flash, but we also have extended this for, in this work with Fukami and Oshlum from Chicago. We also have extended that for different geometric magnetic materials, and even like with YIG. So we have worked that out, and it seems that YIG can also be like a good system for mediating the coupling and entanglement between two different spins, and we calculate essentially the cooperativity, and again, cooperativity here exceeds like 10,000, just like showing that it's also possible to have this strong coupling between magnon and NV spin. And later on, we also start like to investigate some like dynamics using Lindblad master equations. So we analyzed both like on resonance and off resonance protocol, and we essentially like contrast and compare them. And here is just like a graph summarizing this. So for like both of these two different protocols, we are able to predict the negativity different from zero, violations of Bell's inequality, and also like a finite fidelity. And so on one hand, the own resonance, it gives like a large exchange rate and exchange gate actually, but on the other hand, it gives like a little bit like lower fidelity. So the off resonance, since you're not exciting real magnons, it does produce like better fidelity, but the the entangling gate rate is a little bit like longer, but still both of those two different protocols provide creation of entanglement between two NV spins. And so again, this is also a good proposal for establishing entanglement between qubits. And yeah, so and just like to sum up, I presented what spin defects are. I showed why they're like good qubits. However, we understand what are the problems that they face, okay? And then towards the end, I just proposed one possible way to allow for this entanglement and coupling between qubits through these magnonic modes, okay? And yeah, and with that, I would like to thank you everyone for the attention, and just like leaving here the references, and also I do have open positions here in University of Iowa for this fall and also for 2023. So if you are interested not only on these topics that I mentioned, that I talked and described here, but also in any one of the topics written and showed by this slide, please reach out to me. And yeah, and with that, I would be more than happy to take any questions. Yeah, thanks.
Thank you very much, Denis, for this nice talk. So maybe I will start with a question about the scalability. So all the results you presented were for only 2 entangled qubits.
Yes, that's
perspectives for n larger than 3 or.
Yes, that's a great question, Krisha. So so yeah, as you even said, so this is for only 2, but in this work, I'm just like trying to. Yeah, okay, so it's frozen. Okay, so this is like for 2, but in our PRX quantum paper, we have extended this for a array of, for instance, like more than 10 easily. So 12, for instance, we can see that up to 12 qubits, you can have entanglement and coupling through this magnonic mode. So you just like have a waveguide of YIG, and then you can place like 12 different centers, and up to 12 you can still like have entanglement and coupling between this spin qubits. So up to 12 we're like still like fine, yeah. And but there's always like ways to increase that, yeah.
Okay, thank you. Any other question? You will remember that you are all free. David has a question. You can mute yourself, David. Yes, go.
Hi, thanks. I unfortunately don't have a camera, but I hope you can hear me well.
Yes, I do. Yeah.
Thank you very much for this very interesting talk. I frequently see the field of quantum information and foundation of quantum mechanics well developed, but I do not frequently see discussions between foundations and condensed matter. And it's really nice seeing the development of this. In quantum information, whenever people talk about 2 qubits, in your case, NV number 1 and NV2, and there they usually talk about a decoherent classical communication channel. But in your case, so that's question number 1, the communication is really a genuine quantum channel, as far as I understood, that you call the quantum bus. So is this, there is no decoherence, at least in theory. Okay.
Yep, so you can ask the second one and then I can comment on both of them.
And then the follow-up question would be, so from the perspective of whoever then is measuring NV1 or NV2, what is the final observable? Is it a collective mode of the magnon?
Okay, perfect. Yeah, those are also very good questions. So as for the first, I'm going to comment on your comment. I'm going to comment about your comment. So yeah, so I'm trying like to situate my research within this what we call like interface between condensed matter and quantum information science. So that's why I brought like this, let's say, well, this type of interface view, right? Trying to really implement this type of qubits using condensed matter systems. So now your first question is about the magnon. So the magnons here, they're really like establishing the communication and the coupling between the qubit 1 and qubit 2. However, they can also decohere the system, okay? So if you take a look, for instance, here, when we simulate the density matrix dynamics for these 2 different qubits coupled through magnon nodes, so magnon nodes can also decohere and dephase these things, okay? So that's, and this is of course limited by the number of magnons that you have in your system. Okay, so the larger the number of magnons, the more likely they're going to decohere your system. So so it's important to work to avoid this noise. It's important to work with temperatures up to like 100 millikelvin. Okay, even though those qubits without magnons are robust even at room temperature, to be able to couple them to each other and create entanglement, through magnons, we really need to have like low temperature. Otherwise, the magnon's going to decohere our system. Okay, just like try to think as the magnon as a spin bath. Okay, which is just like fluctuating and oscillating crazily. So this definitely decoheres. But like for our simulations up to 100 millikelvin, actually up to 150 millikelvin, this proposal is shown to be stable, and and therefore the entanglement is established. So I think that I addressed your first question. Now for your second question, can you repeat your second question again? I forgot about it. David? You're muted.
Yeah, sorry, I wasn't able to unmute myself.
Okay, no problem.
The follow-up question was, what is the final observable from the from the guy in the lab?
Yes, that's a very good question. So this goes back to how to read the NV, right? So for instance, you're really gonna like so you're really gonna like shine two lasers independently, okay? And you're gonna like assess what is the readable, it's gonna be the photoluminescence, saying this photoluminescence here, saying whether your state now it's within the plus or minus one, or in the zero state. So it's really like the photoluminescence that gives this information about the qubit being the zero state or the qubit being the one state. So everything is like optically, it's done optically, okay? Initialization and also the readout. So everything is going to be like photons that you collect after emitting a laser to like, to read your system. That's what is interesting about this type of system. Everything is done optically.
Great, thank you very much.
Now Martin has a question. He first say, thanks for the great talk. Could you comment if there are proposals to use phonons as the bus?
Yes, definitely. There are also, I did not mention that due to the lack of time, but yes, actually there are proposals using carbon nanotubes, okay, nanotubes made of carbon, and using the phononic modes of those carbon nanotubes to control and establish this entanglement between two NV things. So definitely, yes, there are also like proposals for quantum bus made of phonons. Yeah.
Okay, great. Any other questions?
I have a question.
Great.
So I assume that for technical applications, eventually you may want to be able to connect and disconnect the qubits, right? So and the bus from the qubits. Is that correct? You want to be able to control the interaction between the two, like, you know, keep the interaction on for a little while and then turn it off. So how would you do that in your context?
Yes, that's a very good question, Adrian. So here we can apply, for instance, electric field, and by applying, I did not mention that, but we can apply electric field in order to tune the resonance condition between magnon and spin frequency transition. Okay, so, and this is essentially like represented by here. This is what we're saying, right? We need to bring the NV1 in resonance with the magnon mode and let it interact for like some time, and then just like bring out of resonance. And this can be done through local electric gates, which are going to only shift the NV spin levels, because the NV spin levels are the only ones susceptible to the influence of the electric field. So just like by applying some gate, we essentially like shift and make out of resonance and on resonance. And so those, we're going to have like essentially local gates here, and right, and local gates like here. And this is what it's going to essentially be controlling this resonance condition. And that's a very important question. This can also be done with strain. Okay, so we can also do that with strain, since and the center levels, they also respond to strain. Okay, so either a strain or electric field, it's going to shift the 0 and 1 to something like this. And let's say that the magnum mode is here, right? Like, so by either strain or electric field, you can essentially shift this and make them to not talk to the magnum mode anymore. Yeah.
Cool. Thank you.
Okay. Any other question?
Yes, I have a follow-up question. Like you just mentioned that these two local gates, that these are two quantum gates?
No, those will be like classical gates in that sense. Yeah, like just like metal, just like think about, yeah, just like metals, and apply a difference voltage drop across the diamond piece. And so it's really like electric field. There's like no, it's just like the classical gates that we use for, yeah, out there. Yeah.
Like in your proposal, like, do you need some quantum gate, or can you comment on this?
Right. So yeah. So sure. So for instance, here we can see the swap gate, right? Since the population between so there's this shift in population of NV1 and NV2. So this is like a swap gate that's being produced by the magnon mediated interaction, right? So so this proposal establishes this swap gate through magnons. So so that's essentially the first gate that we have proposed using this. And with swap, of course, you can like build many others, but we did not explore that too much. But this is here essentially we're like only showing the swap gate. Yeah.
Okay. Thank you.
Sure.
Okay, with that, I think we are all set to thank Denis again for this nice talk and nice discussion, and hope to see you next week for another quantum matter seminar. Bye.
Thank you.
Finishing the meeting. Let me just stop.
Cara, você não vai. O meu. Lembra